Welcome to today's Manufacturing Engineering Media webinar. Our topic is continuous dress creep feed. Hello, I'm Jim Sawyer, Senior Editor at ME Media. Before the presentation begins, I'd like to provide some background on what we will be doing today. Our sponsor, United Grinding, is the North American arm of Korber Schleifring, a leader in grinding machine technology and support. During this webinar, you will learn why continuous dress creep feed is a technology that is enjoying a resurgence. You will be able to ask questions during the presentation using the Q&A box that will appear at the bottom of the screen. Following the pre-recorded presentation, Phil Wiss of United Grinding will join us to answer your questions. If time runs out before we can get to all the questions, we will make sure the answers are emailed to you. As mentioned, the main body of this webinar is pre-recorded. As often happens with viewing videos over the Internet, the quality of the presentation can be affected by the type of Internet connection you have, the amount of total bandwidth available to you, and the number of people accessing that bandwidth. If you experience difficulty, please let us know via the Q&A app. Also, if you have questions about any other aspects of our webinars, please email me at jsawyer@sme.org. Larry Marchand, our presenter, is Vice President of United Grinding Surface and Profile Group. The Profile Group provides custom grinding solutions for the Mayerly and Blome machine families. Larry began his career with United Grinding Technologies in 2000 as a project manager responsible for on-site management at the Pratt & Whitney Turbine Module Center expansion. Larry became Vice President of the Surface and Profile Group in 2010. His involvement with turbine engine manufacturing began in 1984 with GE Aviation. Now, here's Larry.
Hello, this is Larry Marchand from United Grinding Technologies. Today I'm going to speak a little bit about continuous dress creep feed grinding, kind of under the theme of making a comeback for difficult to grind workpieces. I'd like to start by giving a little background on continuous dress creep feed grinding and just maybe take a step back and even phrase up grinding in general and talk about the basic elements of grinding. Of course, grinding is an abrasive machining process that uses the grinding wheel as a cutting tool, and we like to think of grinding as just 1,000 little milling cutters individually working to remove metal from the part. The actual work element of grinding can be broke up into three basic elements. You have cutting, which is obviously the most desired part of the grinding process, where you're actually producing a chip with the abrasive grain. Second element is rubbing. Rubbing is where you're actually kind of pushing through the metal. Unfortunately, this is one of the negative part of grinding. That's where your grain has gotten dull. It's not producing a good chip. Therefore, you're inducing heat and stress into the part surface. The third element is plowing, and plowing is like almost like a deformation process where you're literally pushing the metal across the part. Not enough sharpness or energy in the grain to physically break the chip free, so the chip is being pushed or rolled. The result of this is large burrs. Also, like with the rubbing, plowing also generates a lot of heat and unwanted deformation of the part. So these are the two elements we're trying to avoid. We're trying to really optimize the process to have as much true cutting action as possible. So if we break grinding down into the different types, and pretty much all the grinding can be broke down into three basic derivatives. You have surface grinding, which is the using a formed wheel that's slowly fed down into the part in very small increments as the part oscillates under the wheel. It's usually a very fixed feed rate. Typically, these machines are hydraulic tables with down feed, kind of the very essence of grinding. Dressing is performed at increments set throughout the process. Then you have creep feed grinding, which is using also a formed grinding wheel, but now you're using typically a CNC machine, and you've limited the number of cutting passes because you're actually using a controlled feed rate that may vary from cut to cut, and the depth of cut can also vary based on the amount of wheel load and stresses. So you basically have a process that's kind of more effective than surface grinding and allows you to have a variety of feeds and speeds and depths throughout the process to really optimize the grinding. And then comes creep feed continuous dress, which is characterized by a deep cut at a low speed, typically taking full form shape or close to it, and it's done at a constant infeed of the diamond roll. So you have a diamond roll mounted over the wheel, which I'll get into some examples shortly, that's constantly feeding by a CNC controlled axis into the wheel, maintaining the form and maintaining the sharpness. So again, and with each of these processes, they're all highly dependent on the material type, quality, finish, and form shapes. So that's pretty much grinding at its essence. And again, grinding is defined as a wheel with thousands of small cutting surfaces, and it can be broken down into the elements of the individual grain sizes, creating the cutting force, elements like wheel porosity, which allow cooling to get into the wheel, also allows chip formation and the successful removal of chips, very similar to a flute in a mill. Grinding also has the ability to do complex shapes with very tight form tolerance as a result of diamond dressing. Of course, grinding machines also have the capability to hold tolerances 1/10 of a thousandth of an inch or less due to the precision and rigidity of the machines. And surface finish is also a high value of grinding, where you can reach 16 RMS or better. Again, also a function of material and wheel composition. But so anyway, grinding is a productive process. It has a lot of applications. It typically lends itself more to tight tolerance, surface finish, form, and difficult to machine alloys. So now we kind of stroll up a little bit and look at continuous dress. So continuous dress in its very essence, as you can see from the diagram, is you have a wheel that's basically moving through a part, creating a deep form, and over the wheel you have a rotary dresser. And the rotary dresser is rotation at a prescribed speed, and it's fed into the part at a constant rate. And the CNC control of the machine is compensating for this changing wheel diameter by making incremental movements with the y-axis. So at the end of the cut, you end up with a perfectly flat part while your wheel has changed size throughout the cut. The advantage is the wheel being constantly dressed, you have cutting conditions that remain constant throughout the wheel size range. So your wheel stays sharp, and the dynamics at the part, where the wheel interacts with the part, they stay constant, so you're avoiding things like the wheel dulling and creating more energy and more stress into the part, more rubbing heat. Also, by dressing the wheel constantly, you're creating porosity and openings for the chips to have clearance to get out of the cut. So these are the added values of continuous stress creep feed grinding that kind of set it apart from the other types of grinding, is this ability to constantly sharpen the wheel and constantly maintain the form and accuracy. So if we look at the key elements of a continuous stress system, you'll see here, the first thing is we have a rotary over-the-wheel dresser. In this example, it's a full-form diamond roll, reverse plated type with a predetermined form in it of a tooth shape. So this rotary diamond is turning at a constant speed in a relationship that's pre-programmed to the grinding wheel. And typically the ratio is 0.8. So it's 80% of the wheel diameter is the diameter that we're turning for the diamond roll. Also notice that the diamond roll and the wheel are turning in the same direction. This is called unidirectional. The advantage of that is you're actually kind of crushing or breaking the form into the wheel. What this does is this gives a much sharper, cleaner wheel. It's kind of like breaking a rock. You get nice sharp edges versus trying to grind it. If you go opposite direction, you create more of a grinding motion. So this is crushing. Sometimes you hear continuous stress referred to as crush dressing, but typically it's that 0.8 ratio. That dresser is then infed with you see the blue arrow. That's a precision CNC axis with a very fine resolution feedback, typically 1/10,000th or less of an inch in feed. So as your wheel is rotating, you're infeeding simultaneously at a pre-programmed rate, typically measured in millionths per revolution. So as the wheel is turning, you typically feed in ranges from 10 millionths per revolution to as high as 50, 60 on a really heavy dress, but typically 10 to 20 is the normal range that we use in most of our applications. Obviously, the rotation of the dresser has got to be controlled by a servo motor. It's variable speed because it has to constantly change speed. It has to maintain that 0.8 ratio, but also as the grinding wheel is getting smaller, it's speeding up because the grinding wheel is maintaining a constant speed, what they call surface footage per minute at the contact point of the part. So the diamond roll has to also compensate for this speed change and match the speed of the wheel so it maintains that 0.8 ratio at the interface. So kind of in summary, if you look at the key element, the grinding spindle requires adequate power to dress or crush the wheel shape and maintain that speed. So therefore, the spindle, typically on a creep feed continuous stress machines, you're in spindles that have horsepower in the range of in excess of 50 horsepower up to several hundred horsepower required for this energy. And also the diamond roll drive requires a fairly high torque capability because it's actually trying to restrain itself. While this grinding wheel is trying to crush in, it has a tendency to want to speed the wheel up, and the torque of the dresser motor has to be strong enough so they can hold the speed and not let this grinding roll kind of roll the wheel up and create too much speed at that interface point. So the key elements of the machine, if you look at a couple examples of our Magerle machine, one of the things, it's a very stiff mechanical system. Obviously, there's a lot of forces here. You have the normal force of the part to the wheel, but then on top of that, you have the force of the diamond roller crushing into the wheel. So a stiff mechanical system that has quality vibration dampening. When I say vibration dampening, you're typically looking at systems that are going to create a harmonic. There's a lot of cast iron. There's a lot of steel in a grinding machine. So you need a machine that's dampened in a way that it can control this vibration and not create a chatter system that's detrimental to the grinding process. And of course, as mentioned, you need adequate spindle power. These are best run with direct drive spindles so you don't have any belt slippage or stuff like that. A creep feed continuous stress grinder has a minimum of 4 CNC axes because you have the 4th axis of the overhead dresser, which is always a full CNC controlled axis. And of course, it has to be programmable for all axes so you can develop the programs to control the feed, the speed, and all the different variables of the process. And then, of course, the ball screw, especially on the infeed of the dresser, must be very robust with a very fine infeed because when you're feeding at 20 mils per revolution, that's a really small movement increments, and you want this to have a nice constant feed, no backlash created in the system so you maintain this nice steady infeed for a consistent process. So if we look at a couple examples of continuous stress and where it was really applied successfully, again, you're looking at the form on the right. That's a deep form. That's a classic continuous stress where you've got a very deep form. It's a gear shape, so it's very high tolerance, tight tolerance on the form and the shape. So you need a constant wheel shape. You need the accurate form, a lot of volume removal. It's important to keep the wheel cool because these teeth, as you can imagine, with the wheel straddling on both sides, there's a high probability for burning because you're putting heat on both sides. So by having a porous wheel that's constantly being sharpened, it allows you to keep the cut cool and save any burning. And of course, this is typically a very tough steel that's used in a steering rack system. So it is what they call hard to grind material. It's very difficult to create the chip formation. So again, looking at that, there's a nice real straight-on example of continuous stress showing the ratio of the wheel to the dresser, to the part, and how it's continually compensating. Kind of another element of continuous stress creep feed, evolving around the continuous stress process, but utilizing smart CNC controls, is what we call in-process continuous stress. And if you notice in the diagram, what basically we're doing here is we're intermittently turning on the continuous stress and turning it off. And the theory there is when you have long lengths of cut, you may be overdressing. The wheel may be able to maintain its shape through part of the cut, but it can't quite make the entire cut. So what you want to do is turn the wheel on when you need it, but yet turn it off so that you're saving wheel consumption to make the process more economical. So it's usually done by an active monitoring system. Normally you monitor the spindle power. So typically when a wheel starts to load and get dull, it obviously pulls more power. So when the power consumption goes up, the control monitors this feedback, and you can set a predetermined position, and it will activate the dressing sequence. You'll dress the wheel, the power drops, the dressing stops. So what that does is that optimizes the cost. You have reduced abrasive, You can improve your diamond roll life and also reduce your cycle time. But obviously the biggest one is the wheel consumption and the number of wheel changes, which can be quite time-consuming. But it does require active feedback loop and the diagnostic smart software to be able to do this. The example I show there is a very long length of cut. That's a long roller for the paper industry to create corrugated features. And you can see the grinding length on that is about 3 meters. So it's a perfect example of where intermittent process dress and continuous dress can save wheel and make a viable process. So as we move forward, one more point on grinding in general, just to reference in and frame in continuous stress creep feed grinding. One of the things we use in grinding to kind of baseline grinding one process to another is a term called Q prime. It's specific metal removal rate. Again, it's a relative term used mainly to compare one process of grinding to another, and it's a unit of metal removal per unit time, known as Q prime. And if you see a few examples there, so if you look at surface grinding, you can see the range 2 to 5, and then I put in the third column aero alloys, which is kind of what we're talking about here with the difficult to grind aerospace materials. And you can see it's a 2, it's quite low. Creep feed grinding, you can see that's in the range of 5 to 20. 7 is a norm. Again, this might be a process for a creep feed turbine part. And in continuous stress, you can see the range is much higher, 10 to 50. Baseline about 25 on aero alloys. So you can see it's significantly more productive. And you're going to ask, why do we not use it for all of aero alloys? Well, I'm going to explain that in a minute when we get into some more of the variables within the process. And then, of course, you have CBN, which I've kind of focused on the vitrified, which is dressable CBN. And again, in a range of 5 to 15 with a base of 5. But like I say, CBN also has its own attributes. So you see, looking at grinding across the board, you can see where continuous stress is by far the most productive if you just hone in on metal removal rate only. But we all know that metal removal rate is just one element of the process. So let's take a step back and look at creep feed grinding, continuous stress, where it's come from and where it is today, and just a few bullet points. And again, a little bit of just my assessment, my background. I've been approaching 30 years of working in and around continuous stress creep feed grinding. So this is kind of the way I've seen it grow. Some of you may differ, but continuous stress creep feed grinding was invented in the 1970s. It was actually kind of developed around aerospace alloys. Many of you may know a gentleman named Stuart Salmon. He's still active and about consulting in our industry. He's considered kind of the pioneer of this from his days in university in the UK. So the process was the introduction, what led to the continuous stress was the introduction of powerful CNC grinding machines, along with advancements in CNC control systems that were fast enough to process the information and have the closed loop feedback back to the machine scales and servos. And also there were advancements in grinding wheel technology, the ability of the grinding wheel manufacturers to produce porous wheels, something that hadn't been available at the time. So these three technologies coming together, along with some smart people, put together the process called continuous stress creep feed. Its popularity peaked in the 80s when there were major investments throughout the turbine industry. Massive grinding cells and grinding centers were produced for most of the major OEMs in aerospace. And the anchor technology was always continuous stress creep feed for blades and for vanes. Quite successful at the time, but yet there was really not another process to benchmark it against other than conventional grinding. So then creep feed grinding, continuous stress, then kind of met its foe when CBN technology came out. CBN was introduced, started gaining a foothold, again, as technology improved for electroplating and also dressable bonded products with CBN. CBN at the time provided much better grinding economics. At the time, continuous stress creep feed had very high operating costs. You had high consumable costs with grinding wheels and diamond rolls. You created a lot of waste because not only did you have the swarf or the metal chips, but you had all this dressable grinding grit in the form of waste. So you had the waste haul-off cost. The coolant cost was expensive because these machines typically used high volumes of coolant. So there was a lot of internal, or I should say external factors in addition to the grinding process, but the grinding variables and economics that drove continuous stress creep feed kind of out of favor, and CBN became more of the process of choice within the aerospace industry. It had better economics. On top of that, you had the major push of the aerospace industry in the late 90s to go to lean manufacturing. Lean manufacturing was looking more for smaller machines with single-purpose function that could produce a part in a tack time, not so much a cycle time where you're shooting for the fastest possible cycle, but a tack time, which kind of put a new light on the whole grinding process, where we had always pushed grinding to be the fastest process, when lean told us look at the process as a whole and pace it to the pacing product. So lean machines, they were more flexible, they were smaller. Typically, historically, the continuous stress machines were very large, high horsepower, high cost. So continuous stress creep feed kind of took a back seat and became known pretty much as a niche process, pretty much allocated to applications with very high stock removal or very complex deep form shapes where maybe electroplated CBN couldn't remove the metal due to the chip loading and volume, and dressable CBN also just didn't have the right economics to do such a process. So that's where continuous stress was probably at the beginning of the 2000s. So now here we are today talking about why is there a new interest in continuous stress creep feeding. What we've seen is kind of a small renaissance. I won't say it's replacing some of the other processes with plated CBN and VIT CBN. They still have a niche. But we're seeing, due to a variety of reasons that I've kind of outlined here, and I'll go through, the continuous stress is coming back as a process of favor within the aerospace industry. And if I kind of summarize them, you have the new aerospace material. I think the aerospace industry is constantly striving for the next generation material that can withstand the environment of a jet engine, the temperature, the stresses, the thermal cycles. So new alloys are being developed. These new alloys are constantly presenting new challenges for manufacturing engineers. They become more and more difficult to grind. Some of them become more and more difficult to cast to size, so the amount of volume that has to be removed has gone up substantially on some parts. They have unique surface characteristics that are very sensitive to stress or heat input. So these new alloys are driving a lot of interest in continuous stress. The complexity also of engine parts. Thin walls. Thin walls can be a real challenge if you generate any heat and there's not enough volume in that wall or rail of a part. It can't dissipate that heat. That heat stays resident on the surface and creates a burn, a deformation, and that's a reject. So the complexity of parts is also driving for more sharp, clean, free, cool cutting, grinding processes. And of course, improved abrasive technology. The entire economics of continuous stress grinding has improved substantially in the last 15, 20 years. New abrasives, new bonding technology, new diamond roller technology. So all these have come together to drastically reduce the actual cost of creep feed grinding from the consumable part. And of course, grinding machine flexibility. You know, the grinding machines, like I said, continuous stress machines were very large, expensive. We've been able to package them smaller at more cost-effective price points with additional features for multitasking, tool changing, pallet changing. So the grinding machine has become more of a viable part of the process. And of course, environmental improvements. Again, creep feed machines used to require an enormous volume of coolant, which meant an enormous volume of waste haul-off, and that's a very costly element that we're all trying to avoid. And again, the newer processes, due to the efficiency of the process, require less coolant, and the waste haul-off is also reduced. But by and large, I think the number one is, and the one I'll finish the presentation on, is the stability. Continuous stress, because of the constant dressing, constant sharpening, it is a stable process, 7 days a week, casting lot to casting lot. All the other variables that might go into a grinding wheel, if it's plated, if it's dressable, are eliminated because the wheel in continuous stress is 100% resharpened consistently, and the interaction between the wheel and the part stays constant, fixed, so therefore you have a much stable process. So quickly we'll go through just what are the demands of the new aerospace alloys, and I'll quickly state that it's the extreme temperatures in the operating environment above 1700. In a lot of cases it's well above 1700, it's well in the 2000 plus Fahrenheit range. Also the base alloy elements typically are nickel and cobalt, both of which are very difficult to grind. On a typical turbine alloy, those two elements make up 70+% of the makeup. Plus there's a lot of trace elements within a turbine alloy that also make it a challenge. I mean, typical alloys, trade names, Inconel, Hastelloy, Rene, etc. And these materials are characterized by their ability to withstand temperatures and stresses, but they're also characterized by their rapid work hardening when you try to machine them. They typically have a very elastic deformation that creates rubbing heat and compressive forces into the surface, which are not desirable. Just to give it an example, if you go to one of the machinability indexes, you can see the relationship. Carbon steel, 1212, you see that's considered 100% of the baseline of machinability. Stainless steel, roughly 45. You see Inconel 718, 19%. I've read some of the newer alloys, some of the proprietary specific alloys are down in single-digit machinabilities now. So you see that's ever the challenge to have a process that can machine these difficult-to-machine materials. So again, the new alloys, what are they? They have surface reaction to induced stresses. Minimal amount of excess stress into the part when you're machining can create very negative effects, grain separation, grain pull-out, grain tear. There's a lot of different terms that are used throughout the industry that relate to the negative impact of what can happen on these parts as you apply a cutting tool to them. The whole thing of chip formation, one of the things we're seeing now becoming more and more the norm is single crystal alloys, where you typically have no grain boundaries. The entire part is one grain crystal, which without a grain boundary, which means you don't have a natural fracture point. Normally you would have an induced fracture point where the grain boundaries are when you're trying to create this chip. So now you have to pull this chip out of this solid entity, so to speak. So being able to cut into the metal with a sharp cutting tool point becomes more and more critical because you're not getting a natural fracturing that you might have gotten before. And of course, grain distortion is another key element. If you look at the slide in black and white, right at the top of that little picture there, you can see the grain, but they actually turn to the left at the top. That's a result of the machining process, not a desirable result, but you can see where this grain is so sensitive that it actually changed direction under the force of the grinding process. So very, very challenging. And of course, also with these alloys, there's so many special materials in there, trace elements, so to speak. There's sometimes reactions within the grinding process, whether they be chemical, whether they be mechanical, that creates failures. So the new alloys have increased sensitivity to mechanical and thermal stresses throughout the process. They have very little tolerance for that. So the second thing about the new the resurgence of continuous stress is the complexity of the engine parts. I mean, one of the things we've seen is with the advent of three-dimensional aero design, the design engineers have the freedom to pretty much create any shape they want. The casting companies are getting better and better at casting any shape that's possible. So therefore, now the machining process has to deal with these exotic shapes, very thin walls. So when I say thin walls, it's like the outer band of that vein in the upper right-hand corner, where that may be 40 thousandths thickness after machining. And when you induce heat into that, you also rely on the metal to be somewhat of a heat sink to remove that heat and dissipate it. These thin walls have nowhere for the heat to go. There's no mass there to dissipate the heat. So what happens is you end up with surface burning, surface cracking, and a lot of other undesirable features. Uneven stock distribution, one of the things we're noticing too is some of these materials are so complicated in the casting process, they have to have enormous gating to get the metal in, maybe venting to get the metal out. So when the pour is finished, they remove these gates and vents, and a lot of times these things are quite a bit oversized because they don't want to cut too close to the part, because typically the removal is just a snagging operation. So what you'll see is a lot of stock in very uneven distribution, because it can be at the top of the part, the bottom of the part, the middle of the part, usually at the tip or the root. So gating of the process has created some variability within the process. And of course, larger part dimensions. I mean, in the aerospace industry, there's been a big push for the larger engines, which are bringing parts now, typically in the size of land-based turbines, but yet we now have all these complex geometries that are normal for an aerospace part in parts that are much larger. You have longer lengths of grind, deeper forms than we've seen in the past for a lot of aerospace parts. So the other element that's helping continuous stress make somewhat of a comeback is improved abrasive technology. And what we've seen is, thanks to competition between the major players in the wheel industry, there's been a variety of new abrasive grains, grains with ceramics and extruded and all the different varieties of proprietary and branded technologies that each of the key wheel manufacturers have. And these abrasives have allowed continuous stress grinding to operate at much lower dressing in feed rates. Probably one of the biggest positives has been this wheel technology. And I can say from my experience, when I entered this industry back in the 80s, on a typical continuous stress machine, doing a fairly large turbine part that I was working with, we were fortunate to get 12 to 18 parts per wheel on a wheel that was 24 inches in diameter with an 8-inch bore. And so fast forward now, that same producer producing the same part, they're over 100 parts per wheel. So you're looking at almost an 8 to 10x improvement in wheel life. So that means the economics is substantially better. The waste haul off is reduced. The downtime for wheel change is now reduced by 80%. So you look at all these economics of grinding wheel technology, and they've been one of the prime drivers of continuous stress being now more of a viable process from the economic side. But again, some of the elements of the wheel manufacturers, they improve bond dynamics, bonding of the grains, the porosity, and you see that picture, the upper picture there, you can see the very large pores in that wheel. Those are perfect for bringing coolant into the cut and removing chips out of the cut. I think they're an integral part of a successful creep feed continuous stress job. The ability to hold form, again, that's part of the bonding technology that allows us, again, back to the ability to dress less so we don't have to consume as much wheel. And wheel customers now talk more about cost per part as opposed to wheel cost. I think the newer wheels are substantially more expensive than an old wheel of 20 years ago, but the wheel life greatly outweighs that cost, so your actual cost per part is substantially less. And then kind of the resonating theme is the process stability. I think the quality of the wheels has gotten much better, the balance, the consistency of the blend, and they're able to give us a process that matches the stability of continuous stress. And of course also the diamond roller technology. In the beginning, the continuous stress is very aggressive on the diamond roll because obviously it's continually feeding into the part. And I think early in the development, diamond roll life was a major issue with some complex forms with sharp positive radius corners had very limited life. But now with what they call reverse plated diamond rollers, special technologies with adding reinforcements on corners of diamond rolls, the diamond roll manufacturers are able to give us diamond rolls that now greatly exceed the expectations of the customers for life and economics. So this is a key element of the improvement of the process. And of course, the machine, the grinding machine flexibility. Grinding machines have adapted to the lean philosophy. You're seeing more and more machines that have a smaller footprint where things have been condensed now to meet more of a floor space command to get machines close together for flow of parts. And also the ability to multitask, because one of the things we've noticed with lean is we're seeing lean kind of develop from a true single piece flow to a single process flow where customers now maybe want to do more in one machine rather than do feature by machine to kind of capture the economics of clamping the part one time, a little less operator handling, a little lower chance of misloading if you handle it once versus 3 or 4 times. So the automatic wheel changing has been a key element to be able to change wheels and continuous stress those wheels using an overhead dresser with a double CNC axis is a big push. And again, the multitasking, being able to do continuous stress creep feed grind, and in the same machine, you can do plated CBN. So if you had a groove or a deep form feature, a slot where you needed an intricate shape, you can have plated CBN, you can have milling, drilling. So pretty much the entire abrasive spectrum can be loaded into one machine with the kind of the anchor process being continuous stress creep feed, but the other processes are then added to add more value added to the part. Process monitoring, of course, machine technology now has the ability to monitor the incoming coolant, pressure, flow, use that for control of the process to guarantee that you have a stable, controlled process. Closed loop machining, we can take feedback from offline inspection systems via CMMs, hard gauges, again, making the process more robust and more stable. And then, of course, the ability also to automatically load if a customer were to go that way. So all these features that 25 years ago were not in the realm of a grinding machine, they were more machining center technologies. Now you can see they're all part of the grinding system. And inside the machine, of course, we have the dresser, which is now 2-axis because you have your standard axis that's down feeding into the part. but you also have a horizontal axis in and out that allows you to position the correct diamond roller over the correct roll you're using. We also have fast positioning 2-axis CNC coolant nozzle. Because we're constantly changing wheels, our size range is varying quite a bit, so we have to be able to bring that nozzle back to the size of the wheel that it's just loaded in. So that data comes with the wheel, nozzle lines. It's fast acting, so the nozzle's quickly positioned. And again, elements I said, reduced machine size, reduced coolant, and remote monitoring are all factors and elements that make this process more viable. And the environmental improvements, just a quick note, the filtration technology has improved obviously over the years. We're able to much cleaner refinement of the swarf and the fines to reduce the waste haul off, to make it in a format where it's recyclable, not as much paper or filter paper coming out, so we're getting more true swarf with media-free systems, where now the swarf is reclaimable at a much higher value due to the metal content and lower grinding wheel contact. Plus synthetic coolants, they've also added another element of better economics because they're more cost-effective over the long haul. They tend to have a much longer sump life in the machines, which reduces cost. So again, kind of to summarize, again, the underlying theme is the comeback of continuous dress is the stable process, dependable, reliable. The need to have a wheel constantly dressed that's keeping the cutting conditions constant throughout the entire wheel range. And again, the wheel part dynamics remain constant. That's everything from the sharpness of the grain, the open porosity, the force of the part into the wheel. I mean, one element we've noticed with some other grinding technologies is as the wheel begins to dull, your forces go up, which may change your dimensional qualities of the part because you're pushing a little harder on one side or the other. So you may see your process drift over time as the wheel is not maintaining its sharpness. With continuous dress creep feed, you're maintaining that sharpness. So the process, as it's developed, is a very stable process, both from heat, both from stresses, mechanical, and just a very stable process across the board. So if you look at a couple examples up close, so you can see in the left-hand corner, it's a complex form where we're making quite a deep cut on a turbine blade. Again, removing a lot of material in a very complex angle. Coolant entry is a challenge, so it's a perfect example for a nice porous open creep feed wheel. Center picture, again, we've got a deep cut, high stock removal. That groove is machined pretty much from a solid form there, so the volume of metal is quite high, and it's a long length of cut, so the wheel would have a tendency to load up with chips, and by sharpening the wheel with continuous dress, we're able to keep those chips moving and keep the porosity open. And in a thin wall condition, where the upper right, we're doing the OD of a vane segment, and what we're left behind is that thin wall, which is a convex arc. It's a difficult application to get coolant into. It's also, a thin wall with poor heat dissipation qualities. So again, by having a sharp wheel, we're able to keep that wall cool and keep it burn free. So just to show you one example of a typical application, I mean, the vane there on the left is a low pressure vane. The scope was to grind it complete in one clamping, or excuse me, a 2-machine cell, one clamping per machine. The target was a 16-minute tack time, and a turnkey solution was required with grinding, milling, drilling for a finished part. And the primary driver was the continuous dress, obviously, because we had a lot of material on the ID and the OD. This part had very heavy gates. It was a Rene material, which made it also a difficult alloy to grind. Plus, you can see there was 4 air vent holes on the bottom. There's 4 on the top. Again, they were minor operations to the big picture, but the ability to bring them into the machine was a big savings to the customer to have a nice flow between the parts. Our solution was our Megaly MFP50. It's a 9-axis continuous dress creep feed grinder. The 9-axis comes from 5 axes of the grinding system, plus 2 overhead and 2 on the CNC nozzle. All 9 of those are controlled via the CNC control. We have a 24-position tool changer, pallet system, mill drill capability, 65 horsepower spindle. So it's a very well-rounded grinder for continuous dress and other process to make it a true multitasking, multi-feature process. Again, summarizing advantages of creep feed grinding: high metal removal, long length of cut, thin walls, and material variations. You can see on these examples here's a couple straight-up examples: long length of grind, you're looking at an arc of grind about 9 inches. So that's a long time to keep a grinding wheel buried in a part without the ability to resharpen it and keep it fresh and clean. High stock removal where you have gates and, of course, thin wall conditions. So all these are features to look for and features that are valuable for continuous stress creep feed grinding. So in summary, continuous stress, it's been our view that it's gained a little bit of a comeback in the market. And again, it's driven by the following factors: the demand of new aerospace materials, the complexity of the new designs will foster more the use of continuous stress as a viable process for manufacturing that will be economically justifiable against any other process. Improvements in the overall economics of creep feed, continuous stress. I think now that we're looking past wheel cost, which has been reduced substantially, but also all the other associated costs of a grinding process, the entire abrasive package, the waste creation, tool change, operator intervention within the process. So the overall economics of continuous stress creep feed have come down from probably the most expensive grinding process to now a very viable and competitive process within the choices for grinding aerospace alloys. And then, of course, my underlying theme is the stability, the ability of CDCF to provide a stable process. Constant wheel dressing, producing that sharp, clean, accurate wheel form, that is the number one element to allow this process to stay stable, to stay constant, so that day over day, week over week, you're producing the same quality of parts with no surprises and no rejects for any of the other reasons. So that's kind of the summary, the resurgence of continuous stress creep feed grinder. United Grinding is a supplier of grinding machines of various sizes and capability to do that, and we've been
Hello, this is Jim Sawyer again. We have had quite a good attendance here, and I noticed that some of you joined after the presentation had started. If you would like to catch up on what you missed, in about 3 hours at roughly 6 o'clock Eastern Daylight Time, the presentation will be available in an archived version. Just go through the sign-on process that you used to join us here this afternoon, and you can watch it again from the beginning. And if you would like to share this good information with any of your colleagues, they can also access the presentation in its entirety by going through and registering and watching that archived version. The archived version also has the capability of capturing your questions so we can forward them to United Grinding. So please take advantage of that. We have an advantage here right now, and that is because we have Phil Wiss with us. He is responsible for customer development from Michigan to California for the United Grinding Profile Group. Phil, do you have a question and an answer for us?
Hi, yes, good afternoon. This is Phil Wiss, and a couple questions did roll in that we'll be glad to address right now. And they have to do with a couple of the items that Larry covered in his presentation. The first is, can you utilize continuous stress creep feed with both bidirectional and unidirectional dressing? The basic answer is yes, you can. In general, the difference between bidirectional dressing and unidirectional dressing is the way the diamond roll and the grinding wheel are going. In unidirectional, you have one grinding wheel going clockwise, or one going clockwise and one going counterclockwise. And in bidirectional, you have them both going in the same direction. So there are some advantages to both of those. When you look at bidirectional, what you're looking at is a finer finish on the part. And we also utilize bidirectional a lot of times when we do the initial dress. And it happened, you're introducing a faster dress into the process. So a lot of times we go bidirectional, and it's a little bit easier on the diamond roll. Unidirectional we utilize because it gives us a little bit more aggressive grinding wheel and allows us to remove stock a little bit quicker. So that was the first question, and if you have any additional questions on that, please let me know. The other question was something that Larry mentioned regarding crush dressing. And the question is, what is this? Crush dressing really doesn't have anything to do with continuous stress creep-feed grinding, but it is another means of dressing the grinding wheel. It is done when you have a 1-to-1 ratio between the grinding wheel and the diamond roll, or excuse me, the crush roll. And that is where you take the grinding wheel and you feed it into the crush roll, and the grinding wheel actually initiates the crush roll, and it's fed in, and you're breaking the glass bonds between the abrasive and the other abrasive, giving you a nice sharp form. And this is utilized in a couple different reasons, a couple different cases. One is when it's a high production application and you need extremely tight radiuses, so you get the actual true radius of the grinding wheel grit. And the other reason is when you don't want to invest in a diamond roll, and maybe lead times are a little bit longer. Typically you can get a crush roll developed a little bit quicker, and it's a little bit less expensive than a diamond roll. So for short run production, you could utilize crush roll dressing also. And typically crush roll dressing is done off the table. You need an extremely rigid machine to crush dress overhead, but it is feasible on certain machine tools. And those are our two questions that we had come in. If there's any additional questions, you can either address it directly to United Grinding or go through the website and address them there. We'll be glad to answer your questions.
Very good. Thank you, Phil. And I have not a question but a comment. I have to say that I am rather impressed by the increase in wheel life that has been accomplished over the years, and the effect that has on the overall economics of this type of grinding. That's pretty impressive.
The new developments in grinding wheels has brought continuous stress creep-feed back to life, for sure.
Well, very good. I think from your comments, and as Larry proved with his presentation, manufacturing technology doesn't always fade into the past. What was once old can become new again. To help keep you abreast of the latest in the technology and techniques of manufacturing, SME and Manufacturing Engineering Media have a host of ways by which you can keep abreast of the latest of these, including grinding and process improvement. For instance, in the October issue of Manufacturing Engineering Magazine, we will feature articles on process improvement and finishing, and we have a long list here of upcoming SME events where various techniques and technologies will be displayed. I'd like to thank you for joining us for this Manufacturing Engineering Media webinar today. We hope you found it most informative. Thanks.